Everyone. Today we're going to talk about section 6.1, which is on a new topic called confidence intervals. So confidence intervals have to do with estimating a value that we believe would be correct for a population parameter. So remember, our goal in statistics is to take the data that we have and then to try to expand that to understand more about the population. So for instance, I may sample students at the MAT, but maybe it's not feasible for me to sample every single student. So I'm going to do a random sample instead, and then hopefully that sample will be reflective of the population, and I can learn something about the population overall, even though I haven't been able to actually ask every single person on campus to fill out my survey or something like that. So for our purposes in this class, we're really going to be focusing on means, but there are similar techniques if you want to estimate population parameters such as the proportion or the variance, standard deviation, and things like that. So again, our focus is going to be on the mean. That tends to be a really common parameter that we want to estimate. So we'll do that here, but if you're interested in going and looking at other parameters, then your text does have other sections on confidence intervals that focus on different things like proportions instead. All right, so in this section, we're going to learn an important technique of inferential statistics, and it's how to use a sample statistic to estimate the value of an unknown population parameter. So again, we're using our sample data to learn something about the population. So the first thing we do is we need what's called a point estimate. And we've actually been doing point estimates all along. So a point estimate is a single value for the population parameter. So it's just one value. So if you're trying to figure out the population mean, then what we do is we use the sample mean as our point estimate. Now, the sample mean is also what's called an unbiased estimate. So a statistic is unbiased if it does not overestimate or underestimate the population parameter. So basically, it does a pretty good job estimating the population parameter. I will say that our sample will likely never ever match the exact value from the population. So when we have our sample mean, it could be close to the population mean, but it's not going to be exact. So even though it's unbiased, and again, it gets us in that ballpark of that population mean, it's not going to ever be exact, but it's still a really good estimator. So it does a pretty good job about being close to the population value here overall. Now, the reason that this is an unbiased estimate actually has to do with the central limit theorem that we talked about in the last section. And that's because the mean of all possible sample means of the same size does equal the population mean. So remember when we took all those different samples and we saw that the means form their own normal distribution. So basically that's how we noted it's unbiased. So if we end up sampling multiple times or many, many times over and over again, and we took the average of all those means, we would get the population mean. So it does, again, if you have lots of samples and you're willing to do this over and over again, really target that population mean pretty well here. So the sample mean is an unbiased estimator of the population mean. Again, we're letting X bar equal the sample mean, and that mu equal our population mean. So just keep your notation in mind. The other thing to note here is that when the sample mean, the error for the sample mean is decreased by increasing n. Now remember, n is going to be your sample size. So basically, the larger our samples, the more accurate our mean is going to be. That's what that's saying. So there is always an error. So we're never going to be perfect with our sample. It will likely never ever match the population mean exactly, but the larger our sample size is, then the less that error occurs. So we get closer to that population value. All right. So a researcher is collecting data about a college athletic conference and its student athletes. A random sample of 40 students are selected, and their number of hours spent on required athletic activities in 1 week are recorded in the table below. And I just copied this table from your text. So find the point estimate for the population mean for the mean number of hours spent on required athletic activities by all students in the conference. So your point estimate for the mean is just your regular sample mean. So we're just going to do a regular average here. So what I'm going to do is take all of these values, so the 19, the 25, 15, the 21, the 22, etc. I'm not going to write them all out. So I'm going to take all 40 values, add them up all the way to that 21 at the end. And then I'm going to take that sum and I'm divided by my 40 data points that I have here. So when you're finding the point estimate for the population mean, you're just finding your regular sample mean here. So that is our best estimate for that population value. So what you're going to get is 842 over 40, which is about 21.1. And again, this is hours. So for student athletes at this conference, they're spending on average about 21.1 hours in that 1 week doing athletic activities that are required. Now, in example one, the probability that the population mean is exactly 21.1, like I said before, is virtually 0. So again, with a sample, it's very, very, very unlikely that you're going to actually have the exact population mean here. But it's still a good point estimate. It's close. So what we tend to do instead of estimating the mean to be exactly 21 using a point estimate is that we can use an interval estimate instead. And that's what a confidence interval is. It's just an interval estimate. So instead of giving you one specific value for what we think the mean could be for the population, we're going to give you a range of values, which is a little bit more realistic, right? That because again, that 21.1, it's likely that it's not going to be exactly 21.1, but it's probably going to be close to that. So we use an interval instead to estimate that mean. And that's our confidence intervals. That's where this is all going. So to form the interval estimate, what we do is we use that point estimate as the center of the interval, and then we add or subtract a margin of error. So for instance, right, if I'm using this example here, my point estimate is 21.1, and I'm going to use an error in this case of 0.6. And again, we'll talk about a little bit later how we actually will find that error. So for right now, you can just accept it. And to find the interval, what you do is you take that 21.1 and you add 0.6. And we take that 21.1 and we subtract 0.6. And then we put these two values together, and that's going to give us our interval. So there's a few different ways that you can write this. Oops, I'm a little crooked here. Sorry, guys. So one way you can write your answer here, oh goodness, hang on. There we go, is to write that center point of 21.1, and then you can write plus or minus 0.6. So this is a common way that you'll sometimes see intervals written, particularly in like newspapers and on polling. They'll have that point estimate here. So this is your point estimate, which again, for our case, is just that sample mean, and then you have an adding or subtracting of the error. So this is one way that you can write your answer here. Another way we could write it is to actually use our values, okay, which is probably more helpful. So we can say we think our mean is somewhere between 20.5 and 21.7. So that's another way you can write it. And then the third way we could write it using more of an interval notation. If you've come from an algebra course, we have something called interval notation. So it goes from 20.5 to 21.7. And we just use parentheses on either end. So it kind of looks like a point, but it actually represents an interval. So from 20.5 to 21.7. So just another way that we can express this interval estimate. Now, before I show you how to actually find the margin of error, there's something we have to do first. You have to determine how confident you want to be that your interval estimate actually does contain the true population mean. So this is sort of a different idea here, is that we're going to have a level of confidence that our interval estimate actually does contain the population parameter. So remember, when we're using that value 21.1, again, we think that the population mean is around there, but I don't know exactly where it is because I don't have all the population data, so we're estimating. So you want your interval to be wide enough so that you feel confident that the true population mean is actually in there, but you don't want to be so wide that like every number is included, right? So if I'm looking at the average of student works, like I don't want to go from like 15 hours to 35 hours. That's just too big of an interval. So you have to balance between having a high level of confidence that the actual population mean is in that interval, and not having the interval be too wide, right? So you want to have to be a reasonable range there. A lot of times what we do is we will choose confidence levels usually in the 90s. So we will choose a confidence level of 90%, 95% is the most common, or 99%. Those tend to be common, although you could do the 80s as well. And what happens is we're going to see that the higher our confidence is that the interval contains the true mean, the wider it's going to get. So usually 95% is a nice balance where we feel 95% confident that the mean is in there, but the interval is not so wide. Now, because we're only 95% confident, we're basically saying that there's we feel 5% chance that the true mean is not in there, right? So when I do a confidence interval or a point estimate, I am never 100% positive that the population mean really is there. So again, these are estimates, and we can feel very confident, right? A 95% confidence level or a 99% confidence level is very high. But I will tell you in stats, right? We never really prove anything 100%, right? I can give you a good estimate. I can tell you what I think is going to happen. Then I feel pretty confident in my work, but it's never 100%. So again, it's always a balance of having a high level of confidence, but also having an interval that's not too wide, because then that's not helpful either. You know from the central limit theorem that when n is greater than or equal to 30, the sampling distribution of sample means becomes approximately normal. So the level of confidence C is actually the area under the standard normal curve between two critical values. So typically when we do confidence intervals and we shade it in our area on the normal curve, we want it centered. So we don't want it all the way to the right, we don't want it all the way to the left. It is possible to do one-sided confidence intervals like that, but we're not going to do that here. So all of our confidence intervals, we kind of want to be centered around that point estimate, so equally on both sides. So there's going to be two critical values, one on the left and one on the right. And these critical values are values that separate sample statistics that are probable from those that are improbable or unusual. And C is the percent of area under the normal curve between those two values. So I think this will be a little bit easier to see once we actually draw a picture. So we're going to look at C equals 90%. So we're saying that our confidence here level is 90%. So again, we haven't even done the interval yet, but we have to decide firsthand, like what's our confidence going to be on the interval? And usually between 90 and 99 tend to be the most common. 95 is the most common. So we're going to use a 90% confidence level here. So we're going to feel 90% confidence that the interval will contain the true population mean. But of course, there's always a 10% chance that we're not right. So there is always a chance of error here. Now I'm going to start by drawing my normal curve here. And we're using the standard normal, so you have that center at 0. And I want to have 90% of my data here. So, and again, I want it centered in the middle when I do my confidence intervals for our purposes. You can do them one-sided, but we're going to focus on the kind of centers here. So basically you're saying, okay, what is this value and what is this value? And actually they're going to be the same number, just one will be positive and one will be negative because everything is symmetric here. So if I just find one of them, that's really all I need because the other one will be the negative version. Now, because we're doing 90%, that means this area in here is 0.90. So I have 90% of my area here, which means that I'm missing 10%, right? So what happens with that missing 10% is we split it in half. So 5% goes here and 5% goes here. And again, for our purposes with confidence intervals, we're always going to center them, and that missing confidence that we have is going to get split into both tails. So now what I want to do is I want to find these z values. And again, I really just need to find one of them. Usually we find the positive version. So you can either use your table here or you can use your calculator. I'm going to start with using my calculator. Okay, so I'm going to go into my calculator and I'm going to press the second and vars key. And I'm going to select normal CDF, which is the second one down. And remember, you're going to put in your lower bound, your upper bound, the mean, and the standard deviation. Now, this is where it gets a little bit tricky. So I know the shaded area is blue, but if I want to find this z value right here, right, then I'm actually looking at everything to the left. Okay. So I'm looking at this whole area here to the left if I want to find that z value. Okay, so, and the reason we're going to do this is because we're actually going to go back now. So I'm not going to use the normal CDF because I don't have the z values yet. If I had the z values, I would plug them in, but I don't have them. But I want you to kind of see this idea of lower and upper bound here. So I only need to find one z value. I just need to find the positive one. So what we're going to do is we're going to figure out the area totally to the left of that z value. Okay. So think about it. If I have 5% in the right tail, then how much do I have to the left? Well, I have 90% in the middle and another 5% here. So I have 95%. So I have 0.95 is the area to the left of the z value that I want. All right, so what we're going to do, keep going back to second vars, and then I want you to use the one down instead that says inverse norm, because this will allow me to put in the area and work backwards and find my z-score instead. So we're going to use inverse norm. Now, when we use inverse norm, it's always area to the left, mean, standard deviation. So the area to the left of the z value is 0.95. My mean is 0, and my standard deviation is 1. All right, and what I get here is about 1.6448. So this z-score right here then is going to be 1.645 about. Now, normally we round z-scores to 2 decimal places. This is one of those ones that we use a lot that sometimes we do round it to 3 decimal places instead. So to actually answer this question, we're labeling these as z sub c. So z sub c is 1.645. It's this one right here. And then negative z sub c is negative 1.645, which is that one right there. So now if you want to check, you go into that normal CDF and you do your lower bound of negative 1.645 and your upper bound of positive 1.645, our mean of 0 and our standard deviation of 1, you do see you get 0.90, which is that 90% in between. So it's a little bit weird to kind of work backwards right here and look at the area totally to the left of that positive one. But once we have those two z-scores, if we plug it back in using the normal CDF, then I do get that 90% area in between those two. Now, if you're using the table in the back of the book, so I'll just do one with the table. You're going to go into your z-score table. And remember, the area that we're looking for here is the same. So you're still looking for that positive z value. So the area to the left of that one, in this case, happens to be 0.95. So you're going to have to go into your table here. And you're looking for, oh, I'm on the wrong side. Let's do this, the positive side. And you're looking for that value of 0.95. So you want to get as close to it as you can. And you can see, where is it? All right, so you can see it's kind of like right in between these two, right? is 0.9495, 0.9505. So if you scroll up, you'll see that that's right in between 1.64 and 1.65. So that's where we get that value of 1.645, just kind of taking the average between the two for your z-score. All right, let's do another one, because again, these are a little bit tricky to kind of get used to. Okay, just getting my notes there. All right, so now we're gonna do another one. And again, we're gonna do a confidence level this time of 95%. So what I'm doing here is I'm using a strategy to find those critical z values. That's all I'm doing. So I have my center at 0. Now this time I want 95% in the middle. So this is 95%, which is 0.95. And let's think about this here for a second, right? So if this is 95%, then we're missing 5%, right, out of 100. So that 5% has to make up the two tails. So you're gonna have to cut it in half to put half in each tail. So this would have 2.5%, and this side would have 2.5% to give me that missing 5%, right? 2.5 plus 2.5 is 5, plus 95 is 100. So there's the full 100%. And as a decimal, this is 0.025. And then again, this is 0.025 as your decimal here for your area. So we have this z value that we're looking for. So now this is your negative z sub c, and this is your positive z sub c. And again, this is really the one we need to find because it's going to be the same one in either case. So I'm going to start by using inverse norm, and then I can go back and check if I want to with the normal CDF. And keep in mind here, you need to find the area to the left. So it's not going to be 95. You want to figure out this whole area to the left. So you have 95% plus another 2.5%. So the area to the left is 97.5% or 0.975. So I'm going to type in my inverse norm function again. Let's see, inverse norm. My area to the left is 0.975. My mean here is 0, and my standard deviation is 1. And I get about 1.9599. So this z value is about 1.96. So here, this one is 1.96, and then this one is going to be negative 1.96. So those are our critical values for this region. And again, if you don't like the calculator, you can do the same thing in the table. So you're going to go to your table and you're going to find the area that's 0.975, and you should see it lines up with a z value of 1.96. Now, if you want to check this, although you don't have to, if I do that normal CDF and I use my lower bound here of negative 1.96 and positive 1.96, with my mean and my standard deviation, you'll see that you get 95, which is the area in between. So it does check out. Again, it's a little bit weird because you have to find one of the z values first using inverse norm on your calculator. And then you don't have to, but if you want to check it, you can use those as your 2 bounds and see that it actually does relate to 95%. Now, there are other confidence levels too, but the main ones we're going to see are 90%, which we just did, 95%, which we just did, and 99%. Those tend to be the 3 most common ones that we use when we're talking about confidence intervals. So these are ones that you may just want to write down or have memorized. So when you're looking at a 90% confidence level, your z-score is going to be 1.645. When you're looking at 95%, you're going to use 1.96. And then for 99%, I didn't do this one, but you can try it at home. It's 2.575. So these are very common confidence intervals that we're going to be learning how to find. So if you see these confidence intervals in this chapter in 6.1, so 6.2 is a little bit different, but in 6.1, these are the z-scores that you're going to end up using in the formula. If you have something different, like if they ask you for 80% or like 93%, then you're going to have to go through this process and find the z-values on your own. All right, so now that we have our z-values, let's pause this video, and in the next video, we'll actually go through the full process.